Hello, this is Sarmad, and in this lecture we'll be discussing the common gate stage. Well, in the common gate stage, the input is being applied to the source terminal of the Mosfet, and the output is being sensed as the drain. And as the name suggests, the gate is common to both the input and the output sides. This is one of the configurations of common gate. Again, we can see that we have a resistor RD that is connected between VDD and the drain, and we sense the output from the drain terminal of the MOSFET. The input is applied at the source terminal of the MOSFET. There's a piece of information that I'd like to share with you guys, and that is in 90 to 95% of the cases we use common source stage, and in the remaining 5 to 10% of the cases we use common gate stage. Now let's try to draw the small signal model for this common gate configuration that we will later use in calculating the voltage gain, input impedance, and the output impedance. Now as we have the n-MOS device being used here, so let's just draw the small signal model for the n-MOS, assuming that there is no channel length modulation. So we have GM V1, and then we have this voltage V1. So this is our drain terminal, this is our source terminal, and this is our gate. So now that we have the small signal model for n-MOS, let's populate the rest of the small signal model with the components that are left in the circuit. Like RD is connected between the drain and the VDD. The VDD terminal is going to go to the AC ground in the small signal model. So we'll have RD coming from drain into the AC ground. The input is applied on the source side. So let's just apply the input at the source side. And the output is sensed from the drain. The gate terminal of the common gate stage is connected to the ground via V0, where the V0 is a constant voltage supply, and as we know that the constant voltage source goes to 0 in the case of small signal model, therefore the gate terminal goes straight into the physical ground. So this is our small signal model that we'll be using to derive the voltage gain, the input impedance, and the output impedance. So now that we have drawn the small signal model of common gate configuration, let's just use it to find the voltage gain of the common gate configuration. Here we can observe that V1 is equal to the negative of Vin. This is because that the positive terminal is on the ground, whereas the negative is on the ground for the Vin, and these two terminals, this terminal of the Vin is connected with this terminal of the V1. Therefore we can say that V1 is actually equal to negative Vin. Now let's just apply a KCL on this node. Here we can see that if the voltage across RD is V out, and the current that is going to flow through this branch is going to be equal to V out over RD, and the current that is flowing through this branch is equal to GM V1. And now that we have the value of V1, which is minus Vin, therefore the current through this branch is going to be equal to GM Vin with the negative sign. So now let's just apply a KCL here. So applying the KCL at this node, let me just label this node. What we get is the current entering the node must be equal to the current leaving the node. So let's just say the current leaving the node is V out over RD plus minus GM V in, and the current that is entering the node is equal to 0 because there is no current entering the node. Now if I rearrange this equation, I'll get V out over V in to be equal to GM RD, and the ratio of the V out and the V in is the voltage gain. Now this is quite an interesting relationship. If you remember, the voltage gain for the common source core configuration was also GMRD but with a negative sign over there. But now in the case of common gate, the voltage gain is positive. So we can make an observation that the voltage gain of common gate is positive. So the next thing we are interested in is finding the input impedance of the common gate configuration. To do that, we need to just presume that all this circuit is enclosed in a black box and only two terminals are coming out of it. One is here, and you can just think of another as the ground. So once we have the circuit in the black box and only two terminals coming out, first we need to set all independent sources to 0. Here we can see that we have got two independent sources. One is the V0 and the another is the VDD. So let's just set them to 0. So we have got RD to the ground, going into the drain terminal of the Mosfet, and then the gate is also going to go to ground for the purpose of finding the input impedance, and on the source side we'll have the input signal. Now after we have set all the independent sources to 0, now let's just try to draw the small signal model of this circuit. And as you can observe from here, that this is a n-MOS. So let's just draw the small signal model for n-MOS first, which is GM V1, where the V1 is the voltage across gate and source, and this terminal is the drain terminal. The RD goes from the drain to the ground, so we have RD goes from drain to the ground, and we can observe that the gate is also grounded. So the gate is also grounded, and for the purpose of finding the input impedance, we have to apply an external voltage source Vx at the input, due to which a current Ix will flow. This blue part is going to be represented in the small signal model over here. Due to which the current Ix flows. Now I can observe that the V1 here is actually equal to minus Vx, which was also the case in the last figure, where we had the same expression when we were finding the input impedance of the common gate. And if I apply a KCL at this node, what I'll get is that the current that is entering into the node is Ix plus GMV1. Now that V1 is minus Vx, so it's going to be minus GMVx is equal to 0. Now if I rearrange this equation, I'll get Vx over Ix equal to 1 over Gm, and that ratio is called the input impedance. So the input impedance of the common gate stage is 1 over Gm. Now remember, the input impedance for the common source stage was infinity. So the input impedance for the common source stage was infinity, whereas for the common gate, the input impedance is 1 over Gm, and that number is somewhere in the range of 50 to few hundred ohms. So now you can pretty much imagine that the input impedance of common gate is fairly small as compared to the input impedance of the common source stage. Now this is a very important observation to keep in your mind. Now we need to find the output impedance of the common gate stage, for which again we have we have to put all this circuit in a black box with only V out coming out of it. So first thing first, we put the circuit in a black box, and in second step we need to set all the independent sources to 0. So the VDD goes to ground, the V0 goes to ground, and the input also has to go to ground. And then we apply external voltage source Vx at the output side, because we are interested in finding the output impedance, and we measure the current Ix that is going to flow due to the application of Vx, and the ratio of Vx over Ix is going to be the output impedance. So here let me just make this figure a bit neat so we can easily understand it. So all these things are grounded. So if I use a black color, that is grounded, and then the gate is also at the ground. Now we need to apply a Vx and measure the Ix, and that the ratio of the Vx and Ix is going to be the R out. Now this circuit is identical to the common source stage we were trying to find the output impedance. So this circuitry is identical to common source stage while we were trying to find its R out. So therefore the R out for this circuit, even if you evaluate it, is going to be equal to RD. So we don't have to do the maths again because it's already been done by us in the past when we're trying to find the output impedance of common source stage. Now let's just do an example where we have assumed that there is no channel length modulation, and the thing I have added over here is the RS resistance, which is going to take care of the non-idealities in the mic, or you can say the input signals. So the question is to find the output impedance of this circuit. Now to find the output impedance, what we have to do is we have to put all this circuit in a box, and in the step number 2 we have to set all the independent voltage levels to 0, including the input signal. So let's just do it. Let's just put all this thing in a box and make all the independent sources set to 0, and that one also goes to ground. And then we have to apply a voltage source externally of Vx, due to which a current Ix flows, and the ratio of Vx and Ix will give us a output impedance. So here we have Rs and here we have Rd. Now if you can go into your memory and try to think what that circuit was, or have we seen this circuit before? Well, certainly yes, we have seen this circuit when we're trying to find the output impedance of common source stage with degeneration. So we don't have to do all the maths again. We can just take the results from there and add it over here. Therefore, the output impedance of this circuit is going to be equal to Rd in parallel with 1 plus GM R naught RS plus R naught. Well, I guess now we have put an R naught over here, so we can just say that lambda is non-zero. That is, the channel length modulation has been assumed in the circuit. Now that we have found the a voltage gain, input impedance and output impedance of common gate, let's see how can we properly bias the common gate stage. As in the case of common source stage, the resistor divider was used. So here we'll also use a resistor divider just to make sure that rather than using two different voltage sources VDD and V0, we only have one voltage source VDD and we generate the V0 from it. So let me redraw the common gate stage. We have VDD over here, we had RD, which was connected to the drain of the MOS. The gate was connected to the voltage supply V0. That was our initial circuit diagram. Now we want to generate this V0 using the VDD only. So what we do is we introduce a voltage divider configuration here. Like this, where we have R1 and R2. So we select the values of R1 and R2 such that the voltage over here is now V0. Well, we can do it easily by using this voltage divider formula. So by selecting the right values of R1 and R2, we can generate a V0 here. So this is the first step in the bias design of common gate stage. So next thing is we need to apply a signal that we want to amplify using this amplifier. Let's just say that we have a signal that is coming from a radio wave and that enters into an antenna. That is a special type of antenna. This antenna takes a radio wave and converts it into the electrical signal. This sort of antenna is called a V antenna. Now V antenna is an antenna which is open circuit at DC. So V antenna is open circuit at DC. That is, if you have, well, you can see from here as well that if there is a DC signal, then this antenna will behave as an open circuit. So now while properly biasing this amplifier, we realize there is no path for the bias current or that ID, which is the DC current or the bias current, to flow through. Actually I made a mistake here. It should be n-MOS rather than p-MOS. So let me just correct this for you guys in in red. So this is n-MOS. So there is no path for the bias current to flow because what we see is the DC current is going to see an open circuit here. So we need to give a path to a DC current to flow and complete the loop. So what we do is we add a resistor on this side to the ground. So now what happens is the DC current ID or the biasing current ID has a path to flow and complete the loop. Well, now that we have added RS to give a path for the DC current to flow through, we need to check if this RS is going to cost us anything. To do that, let's just do analysis. Let's just take a proper model for the antenna. So we can replace the antenna by a voltage source. Let me call this thing V end. And we have an internal resistance for antenna called R end. So this black part is a good approximation for this green antenna over here. After that we have the RS in parallel. So we have the RS in parallel to it, well, in parallel to this thing, And then when I sit over here and look into the circuit, what I see is the input impedance, which we found out to be 1 over GM for this circuit. So I'm going to put a resistance of 1 over GM here. Now let's just assume that the current that is flowing from the antenna is IN, which splits into two paths. One follows this path, which is I1 current, and the current that follows this path is of amount I2. So now here we see that some part of the antenna current, which is coming from the valuable signal, passes through the resistance Rs, which we have used for the bias current to flow. Now that current I1 is an undesired part because we want the complete current from the antenna to pass through the Mosfet. So how do we make sure that the loss of signal is negligible? Well, we just hope that I2 is quite large as compared to I1, and we can make this thing to be true by suggesting that we should pick a RS to be fairly large number as compared to the input impedance of the MOS device, which in this case is 1 over GM. That is, if I find the I2 in this circuit, this is going to be equal to RS over RS plus 1 over GM times I antenna. Now if RS is quite large as compared to the input impedance, which in this case is 1 over GM, then we can say that part turns out to be approximately equal to RS, and that RS cancels out this part, so we will left with I2 equal to I antenna, which is what we want, that all the desired signal must enter into the MOS device rather than get wasted in the RS. Remember that RS is being used to give a path for the DC current to flow, that is this DC ID or the biasing current ID to flow. Now at the end, let's just, for the sake of it, try to find the voltage gain of this common gate amplifier. So before we move into finding the voltage gain, let's just call this node as node X. So we can say that the voltage gain is V out over V in, which we can split using the chain rule as Vx over V antenna times V out over Vx. Here remember that V antenna is actually the V in, so I can just write it as V in, because V in is the voltage that is coming from the antenna. Now what is this quantity? Let me label this thing as 1, and let me find some space to solve it. Well, let's just do it over here. Now if I'm standing over here at this node X and I'm interested in finding the voltage over here, all I see is this as a Vx, and the voltage Vx is going to be equal to Rs in parallel with 1 over Gm divided by R antenna plus Rs in parallel with 1 over Gm. So you can think of a case where I have to find the voltage here, which effectively is these two combined and this one in a voltage divider fashion, and then we have the V antenna or the V in here. So if I bring this V in over underneath Vx, I get my very first expression, which is Vx over V in, to be equal to this part, and this part V out over Vx is already been done, which is equal to the gain of the common gate stage, which we found out to be GM/RD. So if I combine these two results, I'll get AV to be equal to RS in parallel with 1 over GM divided by R antenna plus RS in parallel with 1 over GM times GM RD. So this is my voltage gain, this is my voltage gain for this circuit over here. Thank you for listening.